Hello and welcome to the next submodule in this unit. We're going to start looking at the synthesis script. And again, you'll be expected to manipulate the synthesis script and also understand why the major features there and what they are doing. The synthesis script is as much of your design as the RTL, primarily because it specifies the timing and the timing interfaces to your design. And in addition, it specifies the strategy you want synthesis to use in order to optimize your design. We're going to mainly deal with timing issues here because they're the ones ubiquitous to all designs. So the point is, after synthesis, you'll get a result like this. Here's a schematic on the left, actually in the design analyzer from Synopsys, and the equivalent textual form or the netlist on the right. What a netlist is a list of the standard cell gates that are used. You can see inv x1, NAND 2 x1. Remember, x1 refers to the size of the transistors within the gate, x1 being the smallest gates, using the smallest transistors. On the right, we have a port list, as in the Verilog format we just saw in the test fixture. The dot refers to the port name within the module, in which case is a standard cell. Parentheses is the name of the connecting wire or net within the context of this particular Verilog file. So you can see here net N39, or a net called latch. This obviously kept its name from the original RTL. In the middle you have these U numbers. They refer to the instance name. Notice that each module needs to have a unique instance name. You cannot repeat instance names. So these are the main steps in synthesis. We'll go through the first two of these in this submodule and the last four of them in the next submodule. So the first step is to read in the design, which is more than just a simple parsing of the file. It actually checks for problems, tells you if there are problems that have been identified. And in addition, at the same time, we're going to specify the target library for synthesis. What read actually does is map the design into a library, usually the generic GTEC library that is part of the tool. It is unoptimized at this point. It has not done any logic optimization. The next step is to, in Synopsys terminology, is to specify the constraints. These are mainly timing related. What is the clock? What are the delays on the interfaces in particular? Then in Synopsys terminology, you specify the goals, which usually is to minimize the area. You then optimize the design. This is the actual logic optimization step. And remember, this is the core of the algorithms here, because what they do is they try to produce the minimum logic while also meeting the timing constraints. We then check the timing, set up and hold, get the tool to fix any hold violations if they occur, and write out the netlist. So let's look at the read and the constraints aspects. So the next few slides are going to be quite dense because basically I've just taken the script or a variant of the class script and captured it with comments on the right hand side for the purposes of teaching this. In the top half of this, we're just setting some things that don't matter a lot, except that you'll notice here we're going to set a variable called clock name and a variable called mod name, which is the topmost module of the design. If your clock is different and your count and your design is different, you actually need to change these variables. This is a simple design with only one level hierarchy, so it's fairly straightforward to manage. But in a complex design with multiple levels of hierarchy, you want this to be the top level hierarchy for reasons we'll come to in a moment. We then do the actual read underscore verilog counter.v in the current directory. It's important to actually stop at this point What I suggest you do is, if you're using Design Compiler, cut and paste up to here in and stop and look at the results, because the read is more than a simple parsing of the file. It maps the design into some generic logic and checks for problems and errors. It will give you warnings if there are problems and errors. We'll talk about some examples of these warnings in the next set of notes. If you get these warnings, you have to fix them. You do not have a synthesizable design if these HDL warnings are actually there. The result of the read also gives you a list of all your latches and flip-flops. And it's important to check this for unintended latches. This is easy to do accidentally, to make unintentional latches. How that is done, we'll talk about in the next set of notes. So this is not meant to be a push-button process. You have to stop and look, particularly this result, to make sure that you're going to get a good design. We then set current design to be mod name. What we're doing here is starting at the top of the hierarchy. When you have a hierarchical design, this greatly simplifies the synthesis flow. Unfortunately, the synopsis tool does not analyze the design to work out the hierarchy. If you don't do this, it'll start with whatever the last module that was read in was. Set synthetic library. Things such as adders and multipliers and comparators are obviously not logic gates. They are collections of logic gates designed to perform a function. Synopsys has fortunately provided you with these designs in what's called designware. And this refers to that, to the designware files that contain those. In this particular example, it actually needs the adder from that synthetic library. We then set the target library for the standard cells we're using and the link library, which is essentially the same. And then we're going to start getting to setting the constraints. The first one is the clock period and the clock uncertainty, which is mostly the clock skew. Again, set some variable names, create the clock period $clock per. So what's the clock period here? It is 5 nanoseconds or 500 picoseconds. This sets the period, the clock is having a 50% duty cycle. That doesn't matter much for this design, and assigns it to the clock name clock. You might recall I recommended in the previous notes to actually give your clocks more realistic names. For example, clock 100 for 100 megahertz clock. But in the counter, we just called it clock, so I need to do that here. Next, we set clock uncertainty. This is the clock skew, which we're getting from that particular signal, that particular name. And it's being applied to the clock name of clock. Next, we are going to tell the design what is connected to externally. It needs to know at least the timing behavior of the rest of the world so it can properly calculate timing for those parts of your design, which I've labeled this design here, to make sure we don't get setup and hold violations. The rest of the world has real delays associated with it. The external connections have flip-flops in them, have logic in them, and you must account for these external delays when doing your timing calculations at the input and output ports of your design, which again I've labeled as this design here. I've set up some defaults in this script for this. An actual design, these constraints might be different. What I have assumed in setting up this script is that the other modules that are connected to your designs have registers at the interfaces. That is, there is no logic there. This may or may not be accurate for an actual scenario, and you might have to change this part of the script for an actual scenario when you're interfacing to someone else's design. So what I did here, I actually looked up the clock to Q delay of a D flip-flop, added a little bit of extra time for wiring delay, calculate that as its variable IP delay, and assigned that to all the inputs in this design. And I'm saying here the clock going to the external flip-flop here that is originating these signals is being fed with this clock, the clock I've called clock in this design. So the input delay here is basically the clock to Q delay I've specified it as being the clock to Q delay of a flip-flop plus a little bit of design margin. Similarly, the output delay here, which I'm going to apply to my output ports, I'm going to assume the purposes of this design, again this might change once you know what you're really interfacing with. For the purposes of this design, I'm going to use the setup time of a D flip-flop. I looked that up for this library for the worst case condition. These are the worst case conditions. It's 919 picoseconds at 100 picoseconds for wiring delay. Note again, these are initial assumptions only. Calculate what that is. Apply that output delay to all outputs. And again, I'm saying that I'm assuming the clock going to whatever register these signals end up with in the outside design is being fed with the same clock called clock that I'm using throughout my design. So that tells me the delays, the external delays from how late in the clock period my signals will arrive at the input port and how much before the end of the clock period my signals have to leave output port. But I also need to know the drive strength of this unit here and how much capacitive load is being connected to my output ports. So I need to know the drive strength of the gates driving my input ports and the capacitive load connected to my output ports. And that's what I'm doing next. So I'm going to say, because if this is an X4 gate, it's going to drive my design, the load, the capacitive load here, much faster than if it's an X1 gate. So I need to know that. Similarly, if this is a big gate here, it will slow down my drivers driving this design through the output ports. Again, I'm just going to assume these are D flip-flops. I'm going to assume it's the Q pin of the D flip-flop. So I'm going to set the driving cell to the D flip-flop, the Q pin, apply that to all inputs. I'm going to set the load cell as the D input of the D flip-flops under the slowest conditions. I'm going to add in a little extra capacitive wiring load, and I'm going to assume the fan out is 4. That is, this port is driving 4 D flip-flops in parallel. I actually don't know what that is. To some degree worst casing it. If I actually know it is less than 4, I could change this number and get a little bit of extra timing for me to use within my design. I calculate what that port load is. Use set load to apply that port load to all the outputs. So now what I have done is for all my inputs and all my outputs, I've told Synopsys how much delay is external to my design and what the actual gates are that are external to my design, so it can calculate the contribution of the interface delay to the actual driving strength and loads of the actual gates that are involved. And this is very important to get the timing accurate. If I don't do this step properly, I might get setup and hold violations in my final design and not know it until much later in the design process when I do my final timing verification after finishing the layout. At that point, it's a very complex beast to deal with and much more difficult to work out what's going wrong. So it's important to get this right early in the design process. So what I'm going to do now is illustrate this aspect of interfacing to the rest of the world through a couple of sample questions. And these actually are variants of questions I will ask in later quizzes. So I'm going to ask you this question here. With this script and the following delays, what will Synopsys work out to be the max permitted delay for logic 1 and logic 2, which are the combinational blocks within my module. The thing between these vertical bars here is my module. Note, I'm going to ignore drive strengths here. That if I have drive strength and capacitive loads in this calculation, it actually greatly complicates the calculation. So first we're going to illustrate what input delay and output delay is. Input delay is the delay from the clock edge to when the signal arrives at my input port. Output delay is the latest in the clock period. My signal is the difference between when my signal arrives at my output port and the clock edge that is sampling it. So I must understand what these are in order to calculate logic 1 and logic 2. With a little bit of thought, I can apply this equation to logic 1. That is, the clock period must be greater than the input delay plus T logic 1 plus the setup time of the flip-flop plus T uncertainty, which is the clock skew. I put in the numbers. T clock I get from the script. Input delay I get from the script. Setup time and uncertainty I got from up here. Uncertainty I got from the script. This allows me to calculate the maximum permissible T logic 1 as 3.3 nanoseconds. I can set up a similar equation for T logic 2. That is, the clock period must be greater than T clock to Q plus T logic 2 plus the output delay, which includes any setup time. It calculates the entire delay here, plus the clock skew or uncertainty. Again, put in the numbers. Clock period I get from the script. T clock to Q I got from up here. Output delay I get from the script. Uncertainty I also get from the script. That ends up with a T logic 2, again at 3.3 nanoseconds for reasons of symmetry. Let me just show you briefly where I got these from the script. The clock period was down here, given by this calculation. The uncertainty was here, again assigned clock skew, 0.3 nanoseconds. The input delay was assigned here and worked out above. The output delay was assigned here and worked out above. So that is how I could calculate what these delays should be here in logic 1 and logic 2. Here's another question for you. If T logic 2 was actually this amount, and I was telling my neighbor who's designing the module on the right what to set for his or her input delay, what do I tell that person to set? I.e., this is the inverse problem of here. Here, this was someone else's module. I've got to tell that person how long it's going to take from when the clock goes high to when my data will arrive at his or her input ports. And that's what this calculation is. So again, I'm calculating the delay from when the clock goes high to when my signals arrive at my output, which is my neighbor's input. That quite simply is T clock to Q plus T logic 2. Take values from what I know them to be. This works out to 3.681 nanoseconds. So this is what I must do to interface with other people's designs. If I don't do this correctly, I could end up with setup and hold violations. So again, what we've just been through are the two first main steps in synthesis. The read, which also analyzes the design, tells you what are flip-flops, what are latches, and tells you about any potential problems in the design. The next step will specify the constraints. All the constraints here, and all the constraints in general, will be timing related ones, particularly what are the clocks, there's their period and skew or uncertainty, and what are the delays associated with the part of the world that's not part of the design that I'm actually synthesizing here. That finishes this particular submodule. I'd like you to take the quiz and then proceed to the next submodule. Thank you very much.